Hello everyone, it's honor for me to present the first-place solution of OpenLane topology in Autonomous Driving Challenge. Considering that topology reasoning is based on centerline detection and traffic element detection, we develop a multi-stage framework for high performance. I will introduce our work from those 3 chapters, including baseline selection, further improvements, and experimental results. OpenLane Topology Challenge is for advanced research in understanding the structure of road scenes by examining the relationship between perceived entities, such as traffic elements and lanes. The dataset consists of 2,000 annotated road scenes that describe traffic elements and their correlation to the lanes. It comprises 4 primary subtasks, including the 3D centerlines detection, the 2D traffic elements detection, the topology relationship between traffic elements and 3D lane, and the topology relationship between different 3D lanes. The exploration of topological relationships is built upon the foundation of 3D centerlines detection and traffic elements detection. Therefore, the selection of baselines for 3D centerlines detection and traffic elements detection becomes even more crucial. Different from previous 3D lane detection tasks, 3D centerlines often lack conspicuous geometrical features within images. The detection of 3D centerlines rely on surrounding 3D lanes. Consequently, a larger receptive field is needed for 3D centerlines detection. Therefore, we ultimately chose CVPR2023 as the baseline from many excellent 3D lane detection frameworks. As illustrated in this figure, the lane queries within CVPR2023 interact with image features through global attention, possessing a global receptive field. The detection of traffic is equally crucial. Taking into account previous competition experiences, we have opted for the latest YOLO series model, YOLO V8, as our baseline. Compared to other 2D detection methods, it boasts faster speed and more accurate performance. By integrating YOLO V8 and CVPR2023, we have constructed a multi-stage framework and extended it to the prediction of topology relationships. Initially, a pre-trained YOLO V8 model is employed to generate 2D data object queries. Concurrently, the 3D lane queries are fed into the CVPR2023 head to produce 3D centerlines. This design aims to maximize the performance of 2D detection while aligning traffic features with lane features. Based on the features from both tasks, we concatenate the corresponding features and respectively utilize 2 MLPs to predict their respective topology relationship matrices. The positions with topology relationships are assigned a label of 1, while those without are assigned 0. Subsequently, focal loss is employed for supervision. In addition to the overall framework, we have made meticulous adjustments for each subtask as well. For the detection of 3D centerlines, we have converted the anchor lane modeling method in CVPR2023 into Bezier curves. The final lane lines are regressed by predicting the control points of the 4th-order Bezier curves. Moreover, we have introduced augmentation in the BEV space, randomly rotating the 3D lanes. For the detection of 2D traffic signs, we first perform a statistical analysis on the dataset. As illustrated in the figure above, green boxes represent ground truth, while red boxes indicate prediction results. We find that in consecutive frames within the dataset, Some targets may not be annotated in the former frame, but are annotated in the latter frame. This phenomenon of missed annotations can impact the training process of the model. Additionally, the dataset exhibits a relatively severe class imbalance issue. Therefore, when training YOLOv8, we employed certain modifications, such as class-balanced sampling and the use of pseudo-labels. Following our ablation studies and detailed experimental results. Regarding 3D lane detection, progressively increasing the scale of the backbone results in a continuous improvement of the model's performance. Specifically, VIT large achieves a 10% improvement compared to ResNet 50. Moreover, extending the training duration yields an additional 6% enhancement. While employing BDA augmentation contributes a 1% increase. Here is the ablation study for traffic. Lastly, we have demonstrated the results of topological relationships under varying 3D lane and traffic detection performance. The performance of topological relationships will improve as the performance of both tasks increases. In the test leaderboard, we achieved first-place performance, surpassing the second place by 8 points. That is all my talk. Thanks for listening.